Form factor of atomic hydrogen. For the hydrogen atom in its ground state, the number density is n of r equals pi a0 cubed to the power minus 1 exponential minus 2r over a0, where a0 is the Bohr radius. Show that the form factor is Fg equals 16 divided by 4 plus g square a0 square parentheses squared. Okay, so recall that the atomic form factor is an indication of the distribution of electrons. So for a spherical distribution, we had an important result in the lecture notes, and that result was the atomic form factor for the jade atom is given by 4 pi integral from 0 to capital R, the radius of the atom, and j of rho, the electron distribution function, rho square d rho, sine, or let's do this, rho square sine g rho over g rho, which is the sinc function d rho. Okay. And now we're going to adapt this result to the hydrogen atom. So now for the hydrogen atom in the ground state, if we substitute for the number density n of rho, the given expression pi a0 cube parentheses to the power minus 1 exponential minus 2 rho divided by a0, then we're going to have the atomic form factor. Becomes F sub g is equal to 4 pi integral from 0 to capital R rho square pi a0 cube to the power minus 1 exponential minus 2 rho over a0 sine g rho over g rho d rho. So this is once again for a spherical distribution, and if we take r, the radius in which we're assuming the spherical distribution to infinity, we can say that we can find all contributions. So for r greater than the radius of the atom, it will be insignificant, but for mathematical convenience, we can do this. And this will give us 4 pi integral from 0 to infinity rho square pi a0 cube. Now let's also take this g rho into this parentheses to the power minus 1 sine g rho exponential minus 2 rho over a0 d rho. And in order to perform this integral, we can let x equals g rho so that dx becomes g d rho. All right, so now we can continue. The atomic form factor F sub g is 4 pi divided by pi a0 cube, because that doesn't belong to the integral from 0 to infinity x square divided by g square multiplied by 1 over x sine x exponential minus 2x over GA0 dx divided by G. So let's check how we reach this conclusion. We're substituting x equals g rho here. So we will have for rho x over g. So when we see a rho square here, this is going to be x square over g square. So pi a0 cube we have taken downstairs here. And then we have g rho to the power minus 1, which is x to the power minus 1, 1 over x, next term. Sine g rho is sine x. Exponential minus 2 rho over a0. For rho we substitute x over g. So we have exponential minus 2x over ga0. And for d rho we substitute dx over g. So that's what we have here. Okay, and I can see that these pi's will cancel. So 4 pi and pi a0 cube pi, they will cancel. And we can write this also considering the x terms here. F sub g is equal to 4 divided by a0 cube. Now we have a g square here and another g here, so this becomes a0 cube g cube, integral from 0 to infinity. So x squared divided by x gives us x sine x exponential minus 2x divided by ga0 dx. And now, in order to perform this integral by integration by parts, I'm going to call u is equal to x and dv is equal to sine x exponential minus 2x over g a0 dx, so that du becomes dx and v will be the integral of sine x exponential minus 2x divided by ga0 dx. So with that substitution, the atomic form factor becomes 4 divided by a0 cube g cube. We have integration by parts, uv minus integral v du. So u is x, v is integral sine x exponential minus 2x over ga0 dx minus integral v du, integral of integral sine x exponential minus 2x over ga0 dx dx. So this is an application of integration by parts. Now we have encountered this integral sine x exponential minus 2x over ga0 dx. So I want to work on integrals of the form integral e to the ax sine x dx. So what is this integral? And I'm going to call the result of this integration I. All right. And in order to perform this integral, let's do integration by parts. Let u is equal to sine x, du is equal to cosine x dx, dv is equal to e to the ax dx, v is equal to 1 over a e to the ax. All right. And with that, this integral will become uv, so that's going to be sine x divided by a e to the ax, so we're performing integration by parts, minus integral v du, integral v 1 over a cosine, let's see, 1 over a e to the ax cosine x dx. And now let's do integration by parts again. Let u is equal to cosine x du then becomes minus sine x dx. dv is e to the ax dx, and v is 1 over a e to the ax. So if I continue with this, I will obtain the first term, sine x e to the ax over a minus 1 over a. Now I'm performing this integral, integral e to the ax cosine x dx. That is uv, which is cosine x divided by a e to the ax minus integral v du. That becomes plus 1 over a integral e to the ax sine x dx. All right, so this is u times v minus integral v du. We have a minus sign here, so this becomes plus. V is 1 over a e to the ax. Du is minus sine x dx, so we have the sine x dx here. And you can see that I have encountered the same integral here, integral e to the ax sine x dx. So the answer that I'm looking for, integral I, is basically the first term, e to the ax sine x divided by a, minus the second term, e to the ax cosine x divided by a square, and then I have minus I, the integral that I'm trying to calculate, divided by a square. So if I take this into I parentheses, I times 1 plus 1 over a square, so I take this minus I over a square to the left hand side, this becomes e to the ax over a parentheses sine x minus cosine x divided by a. All right, and now what I'm going to do is I'm going to multiply this equation by a square. So if I multiply this equation by a square, this a square will disappear. I will have an a square plus 1 here, and you can see that I will have the right hand side becoming, so this a will disappear, so I will have an extra a here, a sine x minus cosine x, because that a will disappear here. So this integral I times a square plus 1 is e to the ax a sine x minus cosine x. So my final answer for this integral, integral of e to the ax sine x dx, is equal to e to the ax divided by a square plus 1 multiplied by a sine x minus cosine x. So this was a pretty good exercise for performing integration by parts. Okay, so we're going to utilize this result. So if I go back to where I have observed this integral was observed here, integral sine x exponential minus 2x over ga0 dx. So what I'm calling a here is basically minus 2 over ga0. So if I substitute this result for my atomic form factor Fg, So the first term was 4 over a0 cube g cube, so I will start with that. 4 over a0 cube g cube parentheses. Then I had x times this integral, so x times e to the ax is basically exponential minus 2x divided by ga0, that is e to the ax, 1 over a squared plus 1, so that's going to be 1 over 1 plus 2 square, which is 4, divided by g square a0 square. And then I have a sine x, which is minus 2 over ga0 sine x minus cosine x. And this will be evaluated between 0 and infinity. So r was changing from 0 to infinity, remember? So that was this first term, and the second term is here. So let's keep the second term as it is. It's minus integral of integral sine x exponential minus 2x over ga0 dx dx. And if I substitute here x is equal to infinity, you can see what will happen. Exponential minus infinity, this will become 0. If I substitute x is equal to 0 here, now because of this x term here, this is going to become 0 as well. So this term basically gives me no contribution. So the answer for this part is 0. So I'm left with this part of the integral. So atomic form factor f sub g becomes, I have a minus sign there, minus 4 over a0 cube g cube integral 0 to infinity. Now I'm going to perform this integral. So this integral dx is my answer. So 1 over a squared plus 1 is basically 1 over 1 plus 4 over g squared a0 square exponential e to the ax exponential minus 2x over ga0, and then a sine x is basically minus 2 over ga0 sine x minus cosine x dx. All right. So if I rewrite this, atomic form factor is equal to minus 4 over a0 cube g cube. Now you can see here this is basically 4 plus g square a0 square, and then this goes upstairs. So this is g square a0 square divided by 4 plus g square a0 square integral from 0 to infinity exponential minus 2x divided by ga0 minus 2 over ga0 sine x minus cosine x dx. So this g square a0 square will basically get rid of the power here. So I will have minus 4 over a0 g remaining. Okay. So if I distribute this exponential into this parenthesis here, I will have first a factor of minus 2 over GA0. So minus 2 over GA0 multiplied with minus 4 over A0 G will give me, so for the atomic form factor, I will have 8 divided by A0 square G square multiplied with 1 over 4 plus G square A0 square. So this is my prefactor for the first integral. And this is integral from 0 to infinity exponential minus 2x over GA0 sine x dx. That's the first term. And as for the second term, I have a minus sign multiplied with this minus sign gives me a plus 4 divided by A0G multiplied with 1 over 4 plus G square A0 square. Now the integral from 0 to infinity exponential minus 2x divided by GA0, this time cosine x dx. Alright. Now, I have encountered a similar integral. What is this integral? Integral of e to the ax cosine x dx. And I have already performed this integral using integration pi parts. So if you perform the same routine that I have followed here in order to evaluate this integral, you will find that the answer is e to the ax over a squared plus 1, a cosine x plus sine x. Alright, so I look at the first term and the second term separately here. The first term I have integral 0 to infinity exponential minus 2x divided by GA0, that's the first integral, sine x dx. And this is basically using the result I have obtained here, e to the ax over a squared plus 1. So that is exponential minus 2x over GA0 divided by a squared plus 1, which is 4 over G square A0 square plus 1, multiplied with a sine x minus 2 over GA0 sine x, and then I had a minus cosine x, so that is basically minus cosine x. So that's the answer for this integral. This will be evaluated between 0 and infinity. At infinity, because of this exponential term here, the answer is 0. At 0, what do we obtain? Cosine 0 is equal to 1. So you can see that I will get a non-zero term from this cosine 0. So exponential 0 is 1. Sine 0, this term goes away, that's 0. So I will have minus cosine 0 over this term, 4 over G square A0 square plus 1. So I will obtain, because I evaluate at infinity, then I evaluated at 0 and subtracted from the result at infinity. This is 0 minus this evaluated at 0. I have another minus sign here, that becomes plus. So this is going to be G square A0 square. If I take this upstairs, G square over A0 square, 4 plus G square A0 square. So that's going to give me my answer here. G square A0 square, 4 plus G square A0 square. Okay, so we have evaluated at infinity, it is 0. Minus gives us, this becomes plus, this becomes plus, then cosine 0 is 1, exponential 0 is 1, this term goes away, and then we have this g square a0 square divided by 4 plus g square a0 square. So that is basically this part. Now, as for the cosine integral, we have integral from 0 to infinity exponential minus 2x divided by GA0 cosine x dx. And for this one, I'm substituting this result for the integral of e to the ax cosine x dx. That is exponential minus 2x over GA0, a square plus 1, that is 4 divided by a square, a0 square, g square plus 1. Then I have a cosine x, which is minus 2 over GA0 cosine x. Then I have plus sine x. This will be evaluated between 0 and infinity as well. At infinity, we're going to get 0. At 0, this will disappear. This will become 1. We will have cosine 0, but we will have this minus sign becoming plus. So we will obtain g square a0 square divided by 4 plus g square a0 square, and then we will have 2 over ga0, 2 over ga0. All right, so we're done performing these two integrals between 0 and infinity. For this one, we will substitute this result, and for this one, we will substitute this result. Okay, let's do that. The atomic form factor is equal to, so the first term we had was 8 over a0 square g square. So let's keep that here. 8 over a0 square g square. Then we had a 1 over 4 plus g square a0 square times 1 over 4 plus a0 square g square. And then we had an integral of exponential minus 2x over ga0 sine x dx between 0 and infinity. That gives us this result, g square a0 square over 4 plus g square a0 square. So we have g square a0 square over 4 plus a0 square g square. And then we go to the next term. We have plus 4 over a0g multiplied with 1 over 4 plus a0 square g squared. So plus 4 over a0g multiplied with 1 over 4 plus a0 squared g squared. And then we had the integral. This is the integral e to the minus 2x over ga0 cosine x dx from 0 to infinity. And the answer we obtained for this one is here. 2g square a0 square, 4 plus g square a0 square in the denominator, and ga0. So let's put that here. So we have 2 g square a0 square a0g times 4 plus a0 square g square. So this a0 square g square will cancel with this one, and then this a0g here will cancel with and together with this a0g we'll get rid of this g square a0 square, and I will be left with the first term, 8 over 4 plus A0 squared G squared squared, and then I have 4 times 2, another 8 divided by 4 plus A0 squared G squared squared. So the answer is 16 divided by 4 plus A0 squared G squared parentheses squared. And I can see that the atomic form factor varies as 1 over G to the 4th power. So on the other hand, when G is equal to 0, the atomic form factor becomes 16 divided by 16, which is 1. So that's basically all the electrons concentrated at the nucleus. So this result was basically what we were supposed to prove. Okay, so let's go back and see what we did here. We are given a hydrogen atom in its ground state. The number density is pi A0 cubed to the power minus 1 exponential minus 2r over A0, where A0 is the Bohr radius. We were asked to find the form factor 16 over 4 plus G squared A0 square parentheses square. So we started with the atomic form factor for a spherical distribution of electrons. That is 4 pi integral 0 to capital R and j of rho square sine g rho over g rho d rho. This is the answer we had in the lecture notes. And we substitute our electron number density for the electrons. Then we obtain basically a result of this form where we have a rho square pi A0 cubed G rho to the power minus 1 sine G rho exponential minus 2 rho over A0 d rho. So this looks a little bit ugly here. We have substituted for G rho x and for dx G d rho, and we have seen that this integral turns into a form integral from 0 to infinity x sine x exponential minus 2x over G A0 dx. And when we do integration by parts, we can see that we encounter an integral sine x e to the ax dx, where a is minus 2 over G A0. And that integral, integral of e to the ax sine x dx, I have shown by using integration by parts twice here. That is e to the ax over a squared plus 1, a sine x minus cosine x. So if we substitute this result for the integral that we have obtained here and here, basically evaluating this between 0 and infinity with the x term in the front of it, we obtain a 0. So the first contribution is 0. The second contribution basically is something we have to work on. So for that, integral of sine x exponential minus 2x over G A0 dx, we substitute this result, and we basically see that the atomic form factor has two integrals in it, the sine version and the cosine version. If you perform the same task doing integration by parts twice for the cosine version, you obtain e to the ax over a squared plus 1, a cosine x plus sine x. So the first integral that we have here, we have evaluated using the sine result between infinity and 0, and the second integral we have used this result evaluated between 0 and infinity. The non-zero terms come from cosine 0. And when we substitute that result into the full expression for the atomic form factor, we obtain the suggested result, 16 divided by 4 plus A0 squared G squared squared. And the atomic form factor varies as 1 over G to the 4th power, we can say, for large G values. For G is equal to 0, you can see that the atomic form factor becomes 1. So basically, that's when you have all the electrons concentrated at the nucleus.